To increase the efficiency of the gas turbine engine, the air being fed into it must be compressed before it has fuel added to it, and it's burnt in the combustion chambers, and it's subsequently expanded in the turbines. There are two types of compressor being used in engines presently available. One allows axial airflow through the engine, while the other creates centrifugal flow through the engine. In each case, the compressors are driven by a turbine, which is coupled to the compressor by a shaft. The centrifugal compressor is much more robust than the axial flow compressor. That, and the fact that it is the easiest and cheapest of the two types to manufacture, made it the compressor of choice in early gas turbine engines. The centrifugal compressor does, however, have one or two disadvantages, which have relegated it to the second position with regards to its use in large modern engines. Firstly, if we compare two compressors, one centrifugal and the other axial, each having the same frontal cross-sectional area, we would, first of all, find that the axial flow compressor can take in a far greater mass of air than the centrifugal compressor, and secondly, that much higher compression ratios can be attained in the axial flow compressor. Since the amount of thrust generated by a gas turbine engine depends partly upon the mass of air flowing through it, it can be demonstrated that when comparing two engines, each having the same frontal cross-sectional area, the engine which has an axial flow compressor will generate more thrust than the engine with a centrifugal flow compressor. We'll now examine the principles of the centrifugal compressor. The turbine assembly, attached to the compressor by a shaft, converts the pressure, velocity, and heat of the gases passing through the turbine into mechanical energy, which is used to drive the impeller of the compressor round at high speed. Air is introduced continuously into the eye, the center of the impeller, by rotating guide vanes, and centrifugal force causes the air to flow outwards, across the impeller, towards the tip. Because of the divergent shape formed between the impeller blades, the pressure of the air increases as it flows outwards between them. And, because the turbine is adding mechanical energy into the equation, the air's velocity also increases. The air leaves the tip of the impeller and passes into the diffuser section. The diffuser section is a system of stationary divergent ducts. The ducts are designed to convert the kinetic energy of the airstream, its velocity, into potential energy, pressure. As you can see from the graph, in practice approximately 50% of the pressure rise across the compressor occurs in the impeller, and the other 50% in the diffuser section. The compression ratio of a very efficient single-stage centrifugal compressor would be in the region of 4:1. This means that the outlet pressure of the compressor would be 4 times greater than its inlet pressure. To attain greater engine compression ratios using centrifugal compressors, 2 of them would have to be used in series with each other. In practice, it's not been found feasible to use more than 2 centrifugal compressor stages together. Excessive impeller tip speeds and extreme centrifugal loading prohibit efficient operation of a third stage. As a result of this, engine compression ratios of much greater than 12:1 are not considered possible using centrifugal compressors. We'll now examine the principles of the axial flow compressor, which are basically the same as those of the centrifugal flow compressor. The axial flow compressor converts the velocity of the airstream, its kinetic energy, into potential energy or pressure. The means which it uses to achieve this conversion are, however, different to those used in the centrifugal compressor. The axial flow compressor, an example of which is shown here, consists of a number of stages. A stage embodies one row of rotor blades of airfoil section which are fastened to a disc, followed by one row of stator vanes also of airfoil section. The stator vanes are fastened to the compressor outer casing. The spaces between the rotor blades and the stator vanes form divergent passages. A number of discs, the number equates to the number of stages, are fastened together to form an integral rotor drum, which is driven by a turbine. In the rotor blades, which are turned continuously at high speed by the turbine, mechanical energy is added and converted into both kinetic, velocity energy, and potential, pressure energy. Within the stator vanes, the air pressure is increased by the conversion of the kinetic energy into pressure energy. Essentially then, the rotor stages of an axial flow compressor can be seen as doing the same job as the impeller in a centrifugal compressor, while the stator stages of an axial flow compressor can be compared to the diffuser in a centrifugal compressor. The pressure rise across each stage is only quite small, the ratio being about 1.1 or 1.2 to 1. This means that in the first stage, the pressure might only increase by about 3 pounds per square inch. As a consequence of this, in order to achieve the compression ratios demanded by more powerful engines, many rotor stages may be fitted on one shaft, which is driven by its own turbine, as shown here. Assuming that the pressure ratio for each of these 10 stages was 1.2 to 1, the output pressure for this compressor would be in the region of 91 pounds per square inch. This arrangement, where a number of compressor rotor stages on a single shaft are driven by a turbine, is termed a spool. In larger, more modern engines, compressors may consist of up to 3 spools. So effective is this method of compression that in an engine like the Rolls-Royce Trent, compression ratios in excess of 35 to 1 can be attained. In this engine, the pressure rise over the last stage may be greater than 80 pounds per square inch. The high pressures generated can result in compressor outlet temperatures of up to 600 degrees Celsius. Although we have only shown engines which have just centrifugal or axial flow compressors, some lower-powered engines do use a combination of centrifugal and axial compressors. The space between the rotor drum and the compressor outer casing is called the air annulus. To maintain the axial velocity of the air reasonably constant as it passes through the compressor, as it's being compressed into a smaller and smaller volume and its density is being increased, the size of the air annulus must be reduced. This gradual convergence of the annulus is achieved by either tapering the compressor outer casing or the rotor drum, or, in some cases, a combination of both is used. Increasing the compression ratio of a compressor makes it progressively more and more difficult to ensure that it operates efficiently over the whole of its speed range. This diagram shows the vectorial relationship between the axial velocity of the air flowing through a compressor and the RPM of that compressor. That relationship gives us the angle of attack over the rotor blade and determines the pressure zones either side of the blade. If the compression ratio of this particular compressor is designed to be 22 to 1 at 100% engine RPM, then this diagram depicts the volume of a unit of air under normal compression reducing as it passes through the compressor at 100% power. The vectorial relationship between the engine RPM and the airflow axial velocity will give this angle of attack over the rotor blade, and these pressure zones, which are the optimum that would occur at the design point. The design point is that point in the engine's performance criteria where it's operating at its optimum compression ratio, RPM, and air mass flow. The problem which is associated with the compressor operating efficiently over its complete speed range is caused by the fact that the compression ratio of the engine falls as the speed of rotation of the compressor falls, and vice versa. Therefore, when the engine is operating at low rotational speeds, the air is not being compressed so much as at the design point, and the volume which it occupies inside the engine becomes greater and greater. Here the engine has been throttled to 60% of its full power setting, and the compression ratio has now reduced to 11:1. The volume of the same unit of air entering the compressor is larger when compressed only by 11:1 than when it was compressed at 22:1. To get through the compressor in the same amount of time it took when it was compressed at 22:1, the increased volume of air must be moving faster. The changed relationship between the increased airflow axial velocity and the reduced RPM will give a low angle of attack over the rotor blade, which will reduce the size of the pressure zones as shown here. If, on the other hand, the engine is allowed to rotate faster than its design maximum, then its compression ratio will increase accordingly. In this case, the engine is operating at 105% of its optimum figure, and the compression ratio has increased to 24:1. The volume of the one unit of air entering the compressor will reduce further than it would at 100% RPM, because the compression ratio is now 24:1. To get through the compressor in the same amount of time it took when it was compressed at a 22:1 ratio, the decreased volume of air will be moving slower. Once again, the changed relationship between the airflow axial velocity and the RPM will change the angle of attack. But this time, with decreased airflow velocity and an increased RPM, it will generate a high angle of attack over the rotor blade. The reduction in axial velocity happens throughout the compressor. The reduction in axial velocity can reach a point where turbulent airflow and a phenomenon called stall may occur. Stall is a partial breakdown of the airflow through the engine, and is a progressive condition, which, if it's not checked, may produce an event called surge. Surge is a total breakdown of the airflow through the engine, which can, in the worst case, cause the airflow through the engine to instantaneously reverse its direction of flow. Let's examine the phenomenon called stall more closely. We've said that the angle of attack of a compressor blade is the result of the axial velocity of the air passing across it and the rotational speed of the blade. We said that the forces of the air's axial velocity and the engine RPM combine to form a vector, which allows us to find the actual angle of attack of the airflow over the blade. So, a compressor stall can be caused by an imbalance between the rotational speed of the blade and the axial velocity of the air passing across it, which can occur for various reasons, some of which we'll now examine. Use the buttons to increase or decrease the engine RPM and see the effect that has on the blade angle of attack. Excessive fuel flow, which may be caused by abrupt throttle opening during an attempt to gain rapid engine acceleration. The back pressure generated in the combustion chamber may rise to the extent that it will cause a reduction in the axial velocity of the air passing through the compressor. Engine operation either above or below the engine design RPM parameters. Engine overspeed or underspeed will increase or decrease the rotational speed of the compressor blades. Situations which may either increase or decrease the angle of attack to the point where the efficiency of the blade is destroyed, and thus the axial velocity of the airflow is reduced. Turbulent or disrupted airflow to the engine intake. This will reduce the axial velocity of the airflow through the whole of the compressor. Contaminated or damaged compressor components, rotor blades or stator vanes, which will reduce the efficiency of the compressor as a whole. This will cause an increase in the axial velocity of the airflow through the compressor because of the decreased compression ratio. A contaminated or damaged turbine will not be capable of generating the power required to drive the compressor at the correct speed. This will make the compressor incapable of generating a sufficiently high compression ratio, which in turn will mean that the axial velocity through the compressor will increase. Excessively lean fuel-air mixture, which could be caused by abrupt throttle retardation. This will cause the axial velocity of the airflow through the compressor to be increased by the decreasing combustion chamber back pressure. Any of the conditions just mentioned can cause a compressor stall to commence, and as soon as it does, there is a partial breakdown of airflow through the engine. The indications of compressor stall can be any or all of the following: fluctuations in the engine RPM, an increase in the vibration level of the engine, which can generate noise, which may become audible in the cockpit, depending on whether the engines are wing-mounted or rear fuselage-mounted, and an increase in the exhaust gas temperature, otherwise known as EGT. This latter effect, the increase in exhaust gas temperature, is caused by the fact that there is less air going to the combustion chambers. Hence, there is less air to cool the products of combustion, the exhaust gases. Remember that compressor stall is a progressive phenomenon. It could, in theory, initially occur at just one blade, subsequently worsening to encompass the whole of one stage, and then, if nothing is done to prevent it, it can affect the whole engine. The progressive deterioration of the speed of the airflow through the engine caused by the stall phenomenon will eventually cause a complete breakdown of airflow through the engine, which we said was called a surge. In severe cases, a surge could cause an instantaneous reversal of the airflow through the engine, with air being expelled through the engine intake with a loud bang. If surge does occur, the throttle of the affected engine must be closed slowly, and the cause investigated. Surge is most commonly caused by either fuel system malfunction or engine control mishandling. In extreme cases, a surge could inflict such large bending stresses on the compressor rotor blades that they contact the stator blades, with potentially catastrophic results. Apart from the loud noise that usually accompanies a surge, there is a large rise in the EGT, and the resulting loss of thrust may cause the aircraft to yaw. The pilot must always be conscious of the causes of stall or surge if he is to prevent either from occurring. Smooth operation of the throttles, both when advancing and retarding them, will ensure reliable and prompt response from the engine. The pilot must also be very aware of the restrictions which RPM and the ambient density place upon the power plant, and amend engine handling accordingly. Operation of the engine outside the optimum RPM and axial velocity range is inevitable. Although design criteria are, after all, aimed at producing the greatest engine efficiency near maximum RPM, engine operation at power settings below that point has to occur if we are to be able to throttle the engine back from full power. So, engine operation below the maximum power level means that we are committed to altering the rotational speed of the compressor, and also the axial velocity of the air as it passes through the engine. Unfortunately, by doing either of these, we are encouraging the onset of stall and surge. Systems that ensure that surge and stall do not happen have to be fitted to the engine. Here are some of those systems. Variable inlet guide vanes, or VIGVs. Variable stator vanes. Compressor bleeds. Multi-spool compressors. Variable inlet guide vanes, or VIGVs, are fitted to engines which have a particular problem with inherent compressor stall at low RPM or during engine acceleration or deceleration. Variable inlet guide vanes are fitted just in front of the first rotor stage. Variable inlet guide vanes can be automatically pivoted around their own axis to vary the path of the airflow going into the compressor, so maintaining the proper relationship between the compressor rotational speed and the velocity of the airflow through the front compressor stages. At low compressor speeds, the variable inlet guide vanes are angled to impart the greatest amount of swirl to the air, thereby correcting the relative airflow to obtain the optimum angle of attack over the rotor blades. Maintaining this optimum angle of attack allows a smooth and rapid engine acceleration. At high compressor speeds, the variable inlet guide vanes reduce the swirl imparted to the airflow, thereby maintaining the correct angle of attack of the air flowing over the rotor blades. After the first rotor stage has been successfully negotiated, the airflow may still have problems further down the compressor, when the engine is operating at other than its optimum conditions. To minimize those problems, some engines are fitted with variable stator vanes. Variable stator vanes can be pivoted automatically so that as the compressor speed is reduced from the optimum design value, they are progressively closed to maintain the airflow onto the following rotor blades at an acceptable angle of attack. In some engines at low compressor RPM, the relationship between RPM and airflow axial velocity may not be maintained to give the rotor blades the optimum angle of attack, unless some of the excess volume of air is allowed to escape from the intermediate stages of the compressor. If a compressor bleed valve, like the one shown here, is fitted to the compressor casing at a position adjacent to the intermediate stages of the compressor, it can be opened at low RPM and during engine acceleration to allow some of the excess volume of air to escape. This will have the effect of bringing the axial velocity of the air in the earlier stages of the compressor closer to the optimum value, and also of reducing the choking effect in the rear of the compressor. This diagram shows a pneumatically operated compressor bleed fitted to the intermediate compressor section of a bypass engine. When the engine is operating at reasonably high power settings, the high pressure or HP compressor output will be high enough to lift the diaphragm in the actuator valve, allowing high pressure air to maintain the bleed valve closed. Conversely, when engine RPM drops, the high pressure compressor output pressure also drops. Eventually, the drop in pressure will allow the actuator valve diaphragm to fall, and its attached valve to close off the supply of HP air to the bleed valve. Consequently, with its supply of HP air cut off, the bleed valve opens, allowing a reduction in the volume of air through the compressor, which would otherwise tend to choke the flow of air through the engine. This combination of optimum airflow velocity and reduced choking will ensure that compressor stall is less likely to occur during the time the bleeds are open, but there are disadvantages to the use of the system. Opening any compressor bleed, whether it's a bleed used as a stall preventative measure or alternatively a bleed used to supply air for aircraft services, decreases the mass airflow through the engine. A decrease in mass airflow through the engine will cause a drop in thrust for a given throttle position, which raises the engine's specific fuel consumption, or SFC. A decrease in mass airflow also raises the engine's exhaust gas temperature, because the amount of cooling air available in the combustion chambers will have decreased. The design of early axial flow engines was developed by adding more compressor stages on one shaft to obtain higher and higher compression ratios. Unfortunately, having many compressor stages on one shaft makes it increasingly difficult to retain the engine's operational flexibility in terms of being able to operate it over a reasonable RPM range. Compressor blade angles are arranged to give peak engine performance around maximum RPM, when the values of the axial velocity of the airflow and the rotational speed of the blade combine to produce a vector which is the optimum angle of attack of the airflow over the blade. Any reduction of engine RPM changes the symmetry of the vector diagram relating the RPM to the axial velocity. Thus, the angle of attack no longer retains its optimum value. Because of this, compressor stall becomes an ever-present problem at lower engine speeds. So, to overcome the tendency that early axial flow engines had of the compressor stalling at low RPM, designers split the compressor, initially into two separate sections. The two sections were called respectively the high pressure or HP compressor and the low pressure or LP compressor. Subsequently, in later, more powerful engines, designers split the compressor into three sections by adding an intermediate pressure or IP compressor. Each compressor section is driven through a shaft by its own turbine. At any given power setting, the speed of rotation of the compressors increases in proportion to its pressure status. Thus, the intermediate pressure compressor rotates faster than the low pressure compressor, and the high pressure compressor rotates faster than the intermediate pressure compressor. We said earlier that together the compressor, the turbine, and the shaft upon which they are both mounted form a spool. By designing the engine so that, upon closing the throttle, the speed of the low-pressure spool falls off more rapidly than the intermediate pressure and high-pressure spools, it can be arranged that the optimum shape of the vector diagram relating to compressor blade angle of attack can be maintained over a much greater engine RPM range, thus greatly reducing the chance of compressor stall. When referring to the speed of rotation of the spools, it's usual to call the speed of rotation of the low-pressure spool N1, and the speed of rotation of the next spool in the engine N2. If the engine has three spools, then the speed of rotation of what would be the high-pressure spool would be called N3. During the development stage of an engine, or more specifically the engine's compressor, a graph will be plotted using data which includes the maximum compression ratio and maximum air mass flow that the engine is capable of sustaining at a particular RPM. A line is drawn which connects points on the graph which equate to the maximum compression ratio and maximum air mass flow at a number of different RPMs. This line is called the surge-stall line. Engine operation at compression ratios or mass airflow values above this line will promote compressor stall and surge. A line is also drawn connecting points on the graph where the engine is operating at RPMs where the compression ratio and the air mass are proportionally matched. This is called the normal operating line. There is a zone between the stall surge line and the normal operating line which is called the stall margin zone. This zone allows for the compressor efficiency reducing throughout its working life and the inevitable fluctuations which occur in the atmosphere and in the engine fuel system management. Every compressor has an optimum operating point on the normal operating line which represents just one particular compression ratio, compressor speed, and air mass flow. The optimum point is called the design point. Ideally, The design point occurs on the graph where the engine will spend most of its service life, that is, at cruising speed at altitude. An engine operating at compression ratios, mass airflows and RPMs that fall below the normal operating line will be operating below its normal efficiency. For instance, throughout its service life, the compressor efficiency will, for various reasons, including minor blade deterioration and contamination, become lower and lower. This will cause the surge stall line to move closer to the normal operating line, reducing the size of the stall margin zone, and thus reducing the tolerance which was initially allowed for those inevitable fluctuations in the weather and fuel system management. This picture shows the basic methods of construction which are commonly used in compressor assembly. The rotor shaft is supported in bearings and is coupled to the turbine shaft in a manner that will allow minor variations in alignment to be catered for. The centrifugal load imposed on the compressor dictates that the rotor blades are fixed to a disc, which itself is fitted around the rotor shaft. The types of rotor blade fixing methods vary, the most common being that where the root of the blade is shaped to form a dovetail joint and secured to the disc by a pin or locking tab. This picture shows dovetail fixing of the blades in the complete disc, with one loose blade in the foreground which utilizes the fir tree type of fixture. The dovetail method of fixing does not ensure that the blade is held immovable in the disc. In fact, the blades are quite loose until firmly seated by centrifugal force during engine operation. Thus, when the engine is windmilling on the ground, the blades rattle loosely and make a sound which is similar to the noise a bag of nails makes when it's being shaken. It's become more and more difficult on smaller engines to design a practical compressor blade fixing method and, at the same time, maintain minimum rotor disc weight. One way of getting over the problem is to produce rotor blades integral with the disc. This type of blade and disc combination is called a blisk. The stator vanes, similar to the rotor blades, are also airfoil-shaped. They are either fixed into stator vane retaining rings, which are themselves fastened to the casing, or they are fixed to the compressor casing directly, as are these shrouded vanes shown here. The shrouding at the inner ends of the stator vanes prevents them vibrating. The vibration can be induced by the velocity of the airflow over them. At the low pressure end of the compressor, the casing is constructed of aluminium alloy. Further down the compressor, the intermediate casing is manufactured from steel alloys. Around the high pressure section of the compressor, the temperature of the air is so high that nickel-based alloys are the only materials capable of withstanding it. The rotor blades are of airfoil section and are normally made from nickel alloys. They are machined to a close tolerance before being attached to the rotor disc. The rotor blades reduce in size from the front to the rear of the compressor to accommodate the convergent shape of the air annulus, as shown here. Some of the low-pressure stages of the compressor, where the temperature of compression is not too high, may have their rotor blades manufactured from titanium. Indeed, as higher temperature titanium alloys are produced, these alloys are progressively displacing the use of nickel alloys in the rotor blades at the high-pressure end of the compressor. Early engines used aluminium alloys in the manufacture of stator vanes, but it was found that it did not withstand foreign object ingestion damage at all well. Thus steel or nickel-based alloys, which have a high fatigue strength and are less easily cracked or eroded by impact, are now used in the manufacture of stator vanes. Titanium is occasionally used in some engines for the manufacture of the vanes in the early stages of the compressor, but it is not suitable for the production of the smaller vanes further into the engine, where the high temperatures of compression can adversely affect it. Another problem which may occur is that of blade rub, where the rotor blades come into contact with the compressor casing. If blade rub becomes excessive, which might occur through mechanical failure, sufficient heat from friction would then be generated to ignite the titanium. This would, at best, require expensive repairs, or at worst, cause an airworthiness hazard. The high bypass ratio engine's LP compressor blades, more commonly known as the fan blades, were manufactured in early engines from solid titanium, because titanium combines the properties of strength and lightness. A low blade weight is essential if the fan is to be able to withstand the out-of-balance forces which would occur if a fan blade failed. Despite the enormous strength of titanium, the fan blades had to have a snubber incorporated into their design. A snubber is a support, fitted at mid-span, which prevents aerodynamic instability. Unfortunately, it also adds weight, and particularly when two of them are required, as shown in this picture, they interfere with the supersonic flow characteristics of the air at the extremities of the blade. Experiments with new materials, particularly carbon fibre, were carried out, but its flexibility greatly reduced its effectiveness, and its use has largely been discontinued. The greatest advancement has been achieved by fabricating the blade from a honeycomb core sandwiched between two outer skins of titanium, as is shown here. This method of manufacture gives the fan blade added strength with less weight, enabling the introduction of the wide chord fan blade, which is portrayed here. The stability of the blade is ensured as a result of its wider chord, and therefore the snubber is no longer necessary. Accumulation of contaminants in both the compressor and the turbine section of the engine reduces the efficiency of the unit. The contaminants in the compressor, which are mostly salt and pollution from industrial areas, reduce the aerodynamic efficiency of the blades, which increases the airflow axial velocity, lowering the angle of attack over the blade, as shown in this diagram. In the turbine, the contamination takes the form of sulfidation, which is a build-up of sulfur deposits from the burning fuel. Sulfidation destroys the aerodynamic shape of the turbine blades and the nozzle guide vanes, and will, over a period of time, erode their surface finish. If the major cause of contamination is salt ingestion, as might be the case with an aircraft which flies for long periods low over the sea, like this US Coast Guard C-130, then a timely rinsing of the compressor with fresh water can avoid use of harsher treatment which otherwise would be required. A compressor rinse can be carried out either while motoring the engine over on the starter or while running the engine at idle speed. This procedure is known as a desalination wash. This picture shows the setup required for washing an engine on another C-130 aircraft. The wastewater in this particular circumstance contains a percentage of cadmium, hence the requirement for a container for the wastewater. If the contamination has reached the stage where a desalination wash is not sufficient, then the application of an emulsion-type surface cleaner may be necessary. The cleaner may be a mixture of kerosene and water, or either solvent-based or aqueous-based cleaner. These are sprayed into the engine intake under the same conditions as the desalination wash. This procedure is known as a performance recovery wash. The turbine can also benefit from a performance recovery wash. For some engines, frequent applications of the emulsion cleaner may justify an extension of their service life. A more vigorous treatment, perhaps more applicable to centrifugal compressor engines, is that of the injection of an abrasive grit into the engine intake while it's running at an idle power setting. The grit takes the form of broken walnut shells. The Americans use the broken stones from apricots. Unfortunately, because the grit is mostly burnt in the combustion chambers, this method does not clean the turbine components as efficiently as does the performance recovery wash. This concludes the lesson on compressors.